Okay guys, chalo, fair. Now we are on to understanding and working for radix map. Let's get started on the radix map. Okay, first I think part of understanding radix map is understanding how radix sort actually works. Right. Okay. So I think I will implement radix sort for this. I think I want to rename it to radix sort. Let's see. चलो basic library कर लो and then what do I want? Do I want anything else? No, I think I will be do I know how to use the no, okay, but we will go on Wikipedia and we will understand shit, okay, and we'll understand how to use radix sort. Radix sort. Okay. So, in computer science, radix sort is a non-comparative sorting algorithm. It avoids comparison by creating a distributing element into buckets according to their radix. Radix is a position. Alright. For elements with more than one significant digit, this bucketing process is repeated for each digit. Okay. While preserving the order of the prior step until all digits have been considered. For this reason, radix sort has also been called bucket sort. Okay, radix sort and bucket sort are the same. And digital sort. Radix sort can be applied to data that can be stored lexicographically. Lexicographical is the generalization of the alphabetical order of 1 2 3, be the integers, words, punch cards, playing cards, or the mail. Right. Okay, radix sort 1887 came as punch card, first memory efficient computer algorithm. Computerized radix sorts had previously been dismissed as impractical because of their perceived need for available allocation of bucket of unknown size. Seward's innovation was to use linear scan to determine the required bucket size and offset beforehand. Okay, allowing a single static allocation of auxiliary memory. The linear scans close. Counting sort. Yeah, radix sort and counting sort. In the modern era, radix sorts are most commonly applied to collections of binary strings and integers. Alright. It's been shown in some benchmarks to be faster than other general purpose sorting algorithms, sometimes 50 to 3 times faster. Nice. Okay, digit order. Radix sort can be implemented to the start of the most significant or the least significant. For example, 1 2 3 could start with one most significant digit or least significant digit. Alright, LST LST radix sort least significant digit radix sorts typically use the following sorting order. Short keys come before longer keys, and then keys of the same length are sorted lexicographically. This coincides with the normal order of integer representation. Yeah. Okay, LST sorts are generally stable sorts. Stable as in with elements in an order. Okay, stable sort is if there are the stability of a sorting algorithm, I think it was if we have the same number, if it repeats, then like we have 11 three times in an array, and we need to sort it so it won't basically mess it up, I think. Radix okay, most significant digit radix sorts are most suitable for sorting strings of fixed length integer representations. Okay, strings of fixed length integer representation. A sequence like here would be sorted as this. If lexicographical ordering is to sort variable length integer in base 10, then the numbers. Okay, strings. All right. Right. I think this is how like if you will see here. Let me see. And okay, where are my repositories? I need I need more repositories. Okay, which is C, right? Then go to, if you see, like see 10. It's it starts on 10, 1 0, 1 11. This is lexicographical order. Lexicographical order. This is how, see, all the ones come before, like uh, if you think about it, 2, right? I think is there a filter to fix this? There's no filter. However, this is what I'm talking about. If we actually see, we have 2, then we have 2 0, 2 1, 2 2, then we have 3. So this is the lexicographical order. I see. As if the shorter keys were left justified and padded on the right with blank characters to make the shortest keys as long as the longest keys. Yes. MST sorts are not necessarily stable if the original ordering of duplicate keys must always be. Okay, stable sorting is that the original order of the duplicate keys should be uh, justified, or it is, what do we say? It is maintained. Like for example, I have 1 3 11. Let's say I have a 13, then I have another 11, then I have a 20, then I have another 11. So we have 11 1, 11 2, and 11 3. So a stable sort, what it would do, it would maintain the order. Like after sorting, it should be 3, then 11 1, then 11 2, then 11 3, and then we have 13 and 20. However, if the sorting is unstable, it's not stable, then the order would be messed up, right? Okay, which more complicated. Alright, other than traversal order, MST and LST sorts differ in their handling of variable length input. LST sorts can be grouped by length, radix sort each group. Okay, then concatenate the groups in size order. MST sorts most effectively extend all shorter keys to the size of the largest key. Okay, group sort can group by length. Okay, so what it is saying is, for the LST, least significant digit sorting, say we have by the length, right? It can sort by the length. However, for MST, like 3 digits in a two digits and then single digit. But in MST, what it will do is, say for example, we have um, we have this following. Let's add another element. So what it will do is, like say I put 100 here. So what it will do, it will pad the variables such that they are all the length of the largest known element. So it would be 001, 003, 011, and you get the idea, right? Okay. and sort them accordingly, which can be more complicated than the grouping required by LST. Now, however, MST sorts are more amendable to subdivision and what do you mean by amenable? Amenable. Amenable are open, responsive to suggestion. Okay, easy. The more responsive, the more open. MST sorts are more amenable to subdivision and recursion. Each bucket created by an MST step can itself be Radix sorted using the next most significant digit. Right. Without reference to any other buckets created in the previous step. Once the last digit is reached, concatenating the bucket is all that is required to complete the sort. Right. Okay, least significant digit. We start with input list is this. Then starting from the rightmost last digit, sort the numbers based on that digit. Okay. We start with this. Right. Okay, so zeros come before. Then we get the twos. Right. Okay. Then sorting the next. Then we have the second. Okay, 2, 2, 0. And finally, notice that an implicit 0 is pre-painted for the two twos so that 802 maintains its position between them. Right. Stable. And finally, by the leftmost digit. Okay, now we have sorted it. Right. Notice that a 0 is pre-painted. Each step requires just a single pass over the data, since each item can be placed in its bucket without comparison with any other element. Some Radix sort implementations allocate space for buckets by first counting the number of keys that belong in each bucket before moving keys to those buckets. The number of times that each digit occurs is stored in an array. Okay, the number of times that some Radix allocate space for bucket by first counting the number of keys that belong. Okay, before moving keys into those bucket. Although it is always possible to predetermine the bucket boundaries using counts, some implementations opt to use dynamic memory allocation instead. Right, most significant digit, forward recursive input, fixed length. Right. Okay, we start with the first digits. Notice that 170 and 802 are already complete because they are all that remains in their bucket. So no further recursion is needed. Okay, next digit. Complexity and performance. Tree based Radix sort, RadixMap, Radix tree. Right. Okay, they don't show implementation, right? Okay, so I have an array of, let's say, 6 numbers, right? 3, 4, 1, 1, 6, and 2. Now, how would I go on sorting it? Okay, so we'll find the largest element in the array, which is 802. It has 3 digits, so we'll iterate 3 times, once for each significant. Okay, so the first step is to find the largest element in the largest. Sort the element based on the unit place. We use a stable sorting technique such as counting sort. Okay, you sort the digits at each significant place It's important to understand that the default implementation of counting sort is unstable. That is, same keys can be in a different order. We can iterate the input in reverse order to build the output rate. To solve this problem, we can iterate the input array in reverse order to build the output array. This strategy helps us to keep the same keys in the same order as they appear in the input array. Sorting based on the unit place. Okay. Perform counting sort in the array based on the unit place. The sorted array is this. Then sort the elements based on tens digit. Okay. We get max. Alright. You get the max. Right. Then it applies a counting sort algorithm, and I know nothing of counting sort algorithm. So for that, so in order to understand radix sort, I must understand count sort first. Okay, so I think, haven't I already done count sort? I feel like I have done it. It must be here somewhere. She taught us in 5th semester, and I feel like experiment. I feel like okay, quick sort and subset problem. Then we have knapsack problem. I feel like I have done count sort somewhere. Depth first search, Dishkastra. Why do I feel like I've already done count sort? However, was it in unit 1? Could be. Okay, doubly linked list. I don't think I will have it here. Yeah. Okay. So, practice. VS Code assignment 1. Assignment 1. I'm wasting my time over this. Collaborate bucket sorting. Yep. Okay. I don't have the PPTs and all, right? Right. No problem. Let's count sort. Let's learn about counting sort. Okay, what is counting sort? In computer science, counting sort is an algorithm for sorting a collection of objects according to keys that are small positive integers. Okay, they should be small positive integers. That is, it is an integer sorting algorithm. It operates by counting the number of objects that possess distinct key values. Okay, we first count the number of objects with distinct key values and applying prefix sum to those counts to determine, okay, we apply a sum on those counts to determine the position of each key value in the output sequence. Its running time is linear in the number of items, and the difference between the minimum and maximum key value. Okay, so it is only suitable for direct use in situation where the variation in key is not significantly greater. Okay, like we don't have extremes, right? It is often used as a subroutine, yes, in Radix sort. Another sorting algorithm which can handle larger, which is another sorting algorithm which can handle larger keys more efficiently. Counting sort is not a comparison sort. It uses key values as indexes into an array and n log n lower bound, omega n log n lower bound. For comparison, sorting will not apply. To an array and the lower bound for comparison sorting will not apply. Okay, lower bound will not apply. Bucket sort may be used as a used in lieu. What does lieu mean? Lieu is instead. Okay, I think you should have used instead, but I guess used instead of counting sort, and entails a similar time analysis. However, compared to counting sort, bucket sort requires linked list, dynamic arrays, or a large amount of pre-allocated memory to hold the set of items within each bucket. Whereas counting sort stores a single number, the count of items per bucket. Okay, input and output assumptions. In the most general case, the input to counting sort consists of a collection of n items, each of which has a non-negative integer key whose maximum value is at most k. Okay, k is our maximum value. In some descriptions of counting sort, the input to be sorted is assumed to be more simply a sequence of integer itself, right? But but this simplification does not accommodate many applications of counting sort. For instance, when used as a subroutine in Radix sort, the keys for each the keys for each call to counting sort are individual digits of larger item keys. It would not suffice to return only a sorted list of the key digits separated from the items. Now I do not get this. The keys for each call to counting sort are individual digits of large item key. It would not suffice to return a sorted list of the keys in applications such as, okay, return a sorted list of the, okay, so it is saying that when it is used in Radix sort, right? So Radix sort, it will right, if we have multiple, then it will display, sorry, I get what it said, right? See, okay, while it is used as subroutine in Radix sort, we are provided with a list of individual digits. So for example, if we were to pass the, let me put a 2 here, 0, 10th digit 0 1 2. So if it sorts it, okay, I feel like this example is not clearly good. Okay, we'll start with 30, 120, and then let's say a 45, 12, and then what could be a little 6 here and there. Alright, so say we have to sort this. We provide the items based on the 10th digit. So for 10th digits, 10th 10th position, it would be 3 2 4 1 and 0. So we provide this array into count sort. Then what count sort does is, if it only returns a sorted list, so it cannot do that, however, it should not do that. It does not suffice. So this is the sorted list. However, what it will return is, it should return is position, that this element is at position 0, this element at position 1. So that is what it means to say. It would not suffice to return only a sorted list of the key digits separated from the items. In applications such as in Radix Sort, a bound on the maximum key value will be known in advance, alright, and can be assumed to be it can be assumed to be part of the input. It can be assumed to be part of the input. See, isn't it really like fascinating? Because count um, count sort by itself, right? Count sort by itself, the k is a maximum element. It's a bound, max, max minus min. I think difference, or I'll get But if in general we have this many values, and the count the count for these k for these is a huge number, that means we have to allocate a big k, right? However, while being used in RadixMap, what it will do is, the limit is usually 0 to 9. It could not grow bigger than that. That's the limit. And that's fascinating, I think. Okay, so it will be known in advance and can be assumed to be part of the input to the algorithm. However, if the value of k is not already known, then it may be computed as a first step by an additional loop over the data to determine the maximum key value. Right, the output, okay, so the k is maximum key value. The output is an array of the elements ordered by their keys. Because of its application to Radix sorting, counting sorting must be a stable sort. That is, if two elements share the same key, the relative order in the output array and their relative order in the input array should match. Right. Okay. So this is the pseudocode. We have a counting sort function which takes the input and the maximum. Right. Count array, we say array of k plus 1 zeros. In output array of the same length as input. Okay, so we first, alright, so this is counting sort. So first is function to compute the max, which is eventually k. So we'll get int find max. We'll take an array and its size, then int max equals 0. Then we will loop through the I less than n and I plus plus. We'll say, okay, running max. Okay, first of all, I will say that max, we will assume that it is the first element of the array. Then we'll go with 1. Then we'll say if array of I is greater than max, right? Then we simply say max equals array of I, and in the end we return max. So this is how I can find the maximum element in the array. So we'll just quickly check. Max equals find max array and size of, I can just provide a size which is 1 2 3 4 5 elements. Let's run it. mm, Radix max. Okay, my bad. Okay, great. Right, I need a poopy break. Alright, I'm back here again. Okay, so हमने ये function बना लिया, and now we move on to, now in the counting sort function we must create two arrays, a count and then right. Alright, so now the counting sort function, which will return an array of integers. So the counting sort will take an array of size n. Right, first find the max element. So we'll go int max equals to find max, and n, we will receive the max. Then create two arrays, count and output of size k plus 1. Now I don't know why we create k plus 1, but k plus the max element k plus 1, and it has to be all zeros, and then output are both of these supposed to be zeros, array of same length as input. Alright, for I equals to length of input minus 1, we put j is equals to key. I need the key of input of I, and count of j is the key, which is the I. Okay, here input is the array to be sorted. Key returns the numeric key of each item. Count is an auxiliary array used to first store the number of items with each key, then after the number of items with each key. Okay, so we have two. Okay, so we are doing -1 for the extra, for accommodating the extra one that we added here. Right. Okay. Output k plus 1, and am I to leave it uninitialized? It's the same. Okay, this is same length as the input, so we'll put n, and arrays of zeros, I figure. Now third step is to obtain the count of each key in the input array. Alright, I get it. See, if we we have the j is the key, right? Key which is the numeric value. For example, for the array that I have over here, keys are 3, 4, 1, and corresponding to them will be the positions, right? 0, 1, we have these positions: 0, 1, 2, 3, 4, 5, 6, and 7. So we'll say, do we have for 0, this is the count input array, and for the corresponding key, which is the value, let me write the input array here. input array is 34162. 34162. Now we will check how many times do they occur in the array. So 3 one time, 4 one time, 1 a single time, 6 one time, and a 2 one time. Right, we have to do this first. Of each element, so for int I equals to 0, I hope they started with 0, and length of input minus 1. Okay, k6 minus 1, k plus 1, 6 plus 1, 7, so 0 1 2 3 4 5 6 7, k minus 1. All right, I think length of input minus 1, even length of input minus 1. Okay, because I here, let me see, okay, I 0 2 length of input minus 1, 2 length of input minus 1. That means if I have say 5 5 and I less than n minus 1, I think that j is equals to key and I want to declare another integer j is equals to 0, then we say j is equals to count of I. J is equal to, sorry, not count of I, j is equals to array of I, and then we'll go count of j is equals to count of j plus 1. This is how we obtain how many times each of the key has occurred. Each key has occurred in the right. Then for I equals to 1 to k, I equals to 1 to k, for the maximum element we go count of I equals to count of I plus count of I minus 1. Okay, so now what we are doing is count of I, say my count array is this, equals to count of I plus count of I minus 1. So we are, if we are at here, then we keep on adding the previous elements, right? Okay, so that is what we are doing. Obtain the running sum of the occurrences of the keys in the count array. So for int I equals to 1, I less than 2k, I think 2k is up to 2 length input minus 1, that is less than length, I think it's less than n, right? that's what it means, and it should be less than k. Then I plus, then we'll go count of I equals count of I plus count of I minus 1. Right. Then we will start from the back. Yeah. K is maximum, values are non-negative. Position where items with each keys should be placed. K is the maximum. Okay. In summary, the input algorithm loops over the items in the first loop, computing a histogram of the number of items occurs within the input. After the second loop, it performs a prefix sum. Okay. Obtain the prefix sum. Prefix sum. The prefix sum, cumulative sum, inclusive sum. Okay, we add computation on count in order to determine for each key the position range where the items having that key should be placed. That is, items of key I should be placed starting in position count of I. Finally, in the third loop, okay, what do we do in the third loop? Output of count of j equals to input of I. Okay, we keep on subtracting 1 down to 0. Input length I n minus 1 because it is the index, minus 1 down to 0. Okay. We will start from the back. Now what is this? What is this? What is this? For I equals to length input minus 1 down to 0. Okay, we are starting from the back. J is equals to the key, and we figure that count of j equals to count of j minus 1, and we put that in the input. I don't seem to understand this part. Right, okay. So we find the max element, create two elements of size n and k plus 1. Then to obtain the count of each key in the array, right, we obtain that. Okay, so it says that it creates some sort of a histogram, that after the count, right, histogram, right, we have 0, then we have 1, right, then we have 2, 1, then we have 3, we have nothing, then this. Then what we do, this is histogram, then we do a prefix sum, which is let me look at the counts. Let me take a look. Ooh, I want to loop it over. For int I equals to 0, I less than size of, I think I know the size, which will be less than k plus 1. I plus plus, I want to print element with count of I. That's all. Let's forget about this for a while, and I want to call Couting Sort on array 5. Let's try and run this. Error. Variable sized object may not be initialized except with an empty initializer. Okay, uh, let me constant k. Okay, right. Do I have to loop it over and set all of these equals to? I think so. Variables cannot be initialized. 2.1. Set all the digits to 0. The counter is set all the digits to 0. Alright. I think I can just do this and then put count of I equals to 0. Right. Okay, so at 0th position, okay, so we have this. This is the count array, which is, let me just get it. So up till now, my count array looks like this. Which is 0, 1, 1, 1, 1, 0, and then 1. So at these positions 0, 1, 2, 3, 4, 5, 6. Okay, so right, it looks perfect because according to the array that I have here, we have the elements 1, 2, 3, 4. We don't have a 5, we don't have a 6, and neither do we have a 0. So it looks perfect. Now after I perform the sum, what will it look like? Right. I perform the sum. Okay. 1 again up to. Alright. Okay, I think this don't look good because I need to go over, so it should actually, because yeah, k plus 1, that is the size, that's my fault. So now it should look something better. Right. And 5. These are the position after the prefix. After prefixing prefix sum, we get count equals to 0, 1, that is 1 plus 2, then 3, then 4, then 4, and then finally 5. Okay, now we move on, and here what do is we set I equals to length of input minus 1, right, because size to index, and then down to 0. J is a key. J is a key. And okay, so what we actually have obtained is that, right, in the array, that should be at position 1, index 1. This should be at index 2. This should be at index 3. This at 4. This at 4, since we don't have this. And this should be at 5. So we start it. Let me just right. Okay, so we start I from length of input -1 down to 0. We find j, which is input of I. So what is basically j? It is the, then we search that. Okay, because we have added an additional, because we are changing the position. Okay, the reason why we are subtracting this one here is because we are basically changing position down to index, because the indexes are based on 0, 1 and all. See, in something like Lua, I wouldn't think we would need this -1, because their arrays start from 1. So actually your index, we subtract 1. Then we obtained that this should be at position in the input array. Input array, we get that this this key should be at index this. This key should be at index this. This key should be okay at index right. Okay, so we now we convert the which obtains the position of the elements in the input array, obtains the positions. Now we convert the positions to indexes and then simply return the sorted array. So how can we do that? We will go for int I equals to length -1 and -1 down to 0. So I should be greater than equal to 0. I minus minus. We obtain, let me set j is equal to 0. We obtain j is equals to a key, which is array of I, right? We're starting from the back, then we check what is the position count of j -1, right? Count of j equals to count of j -1. So here we convert the position to index, then in the output array we search that index, and at that index we put j, input of I, which is basically j, right? So it would be like we put that thing there, easy, and then we simply return the output array. I hope we can return the address to this. return the output, right? Because we are returning a integer pointer, and this will for the lifetime. Okay, maybe I should provide, I feel like I should provide the output array integer, but we'll see. Let me just int star output equals to this, then we simply will go for int I equals to 0, I less than 5, I plus. We can print output of I, and that should do the trick. Let's see. Function return output, yep, return address of output, that is. So how can I change it is I will you must provide an output array, but let me, yes, that is wrong, because these variables, it will destroy itself at the function. So I will create an output array of same length, and initialize all two zeros, and then we'll go output equals this output, then address, now can I get it to point, and I will I think then I feel like there should be a void, and I don't have to return anything, and then start output. I wouldn't need to create it. We create a count. I have an output. I feel like that is all we need. And that's all. Right. Then I would just need to call the function and pass the output array output uh, 1 2 3 4 6, right, correct, there we go. Then the input array, we take the key, okay, position to index, we subtract 1, right. Then in the final loop, we loop over the input arrays, right. We see we first obtain the position from the count array, then we update the position to index, and we update the position to index, and then at that index of the output array, we put the input array element. That is count sort.